Hi, this is Walter, filming in New Orleans. We're on the rooftop lounge of my hotel, the Catahoula Hotel, which is the hippest hotel I've ever stayed at. And there is my lovely wife. You can't quite see her over there. It's a beautiful day here, but it's time for us to do some physics. So we're going to focus down here for the rest of today's lecture. So you'll recall that in the last lecture we were talking about the block wave vector and the tight binding wave function. And so the tight binding wave function, I'll remind you, has the form psi sub vector k, a function of r, is equal to 1 over the square root of n sub l, the number of lattice points, times the summation on j of e to the I vector k dot tj. So tj just means lattice translation vector, and vector k is the block wave vector. You'll hear some noises as I do this, but hopefully you can hear my voice clearly over them. All of that times the atomic wave function phi centered on the point tj. So phi is a function of r minus tj. So we're going to explore a couple of properties of this wave function. And the first thing that we want to explore is the following claim, that changing the block wave vector, so changing the block wave vector k by a reciprocal lattice vector g doesn't change the wave function psi. In fact, we will show that this is true in general. So I'm going to put a starred box around it. But today we are only going to show it for the special case of this tight binding wave function. And on a later day we'll show it more generally. I'll just point out a consequence of this. We've seen this theorem before for phonons, but now we're talking about electrons, and in particular we're interested in conduction electrons, although this theorem would be true for any electrons in the solid. And so the consequence of it means that we can, as we saw for phonons, we can translate any block wave vector back into the first Brillouin zone by adding an appropriate reciprocal lattice vector. So let's prove this, and in our proof we are going to take advantage of the fact that the coefficients that appear in the tight binding wave function represent a plane wave that takes on reality only at the lattice sites. And so the proof of this is going to be really exactly the same as it was for the case of phonons. So if we're using for the tight binding wave function. So proof for tight binding we need to show that, so we must show that psi sub k plus g is equal to psi sub k. So we're just going to take k plus g and substitute it into our expression for the tight binding wave function. And so the only place that k appears in that is in the exponential. So we would get e to the I k dot tj, that's what we have originally, becomes, when we put in k plus g, e to the I quantity k plus g dotted into tj. And we can just factor out the e to the I k dot tj times e to the I g dot tj. And we know from the definition of the reciprocal lattice that g dot tj is going to be just 2 pi times some integer. So e to the I, 2 pi times an integer is just 1. And so that completes our proof. So the conclusion of this is that the meaningful range of the block wave vector k, the meaningful range of block k, is the first Brillouin zone, just as is the case for phonons. And again, we have only proven that so far for the special case of the tight binding wave function, but we will eventually prove that for the more general case. All right, so one of the most important things to understand about any wave function is what is the energy. And this tight binding wave function is only an approximation. So if we are using only a finite number of these atomic wave functions, we're only going to get an approximation to the actual energy eigenstates for the full crystal Hamiltonian. So psi sub k, a little bit of wind here, is only an approximation for the energy eigenstate. And so that means the best we can do for the energy is to find the expectation value. So we can only find the expectation value of the energy. We're not going to be able to get an exact value. All right, I'm going to pause it here. I see that the camera is being blown around by the wind, so I'm going to pause it and try to stabilize the camera, and then we'll pick it up in the next clip.